and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Marianne Freiberger.
And I'm Rachel Thomas.
In this episode, we'll be talking about artificial intelligence, which has made some spectacular progress over the last few years. Rachel, what's the most amazing thing you've come across recently regarding AI?
Well, the most recent thing I heard that was really impressive that I had a look at was something called Sora, which is produced by OpenAI, the people who made ChatGPT. And there's examples. So ChatGPT, you can ask it questions and it returns you text responses very impressively. There's examples of creating images in response to like a text prompt. And what Sora does is it creates video in response to a text prompt. I've only seen the examples that they supplied, but these amazing videos that are so convincing and impressive, and they're produced in response to a text prompt, like 3 woolly mammoths walking across a field, the wind ruffling their hair, and then this incredible short video clip, which has been created by the AI in response to that text prompt. So yeah, that was really, I knew that there was images, and some of those are impressive and some of those are not impressive. And I knew some of the things that ChatGPT was doing, but I didn't imagine that we were at a point where AI was producing video. What are you finding? What's some examples that you've found sort of surprising or alarming?
Well, one thing that sort of made me smile is a good friend of mine recently told me that she was looking through AI-generated imagery, like botanic imagery with flowers and butterflies, like you see a lot in sort of Victorian pictures and things. And she was very impressed by the results that she got, but after a while she realized that some of the butterflies had 5 wings rather than 4. So this sort of illustrates this thing about, if you're learning from data but you don't have structural knowledge, you can make these kind of slightly freaky mistakes, like giving butterflies 5 wings. So I thought that was quite interesting. Now, what powers this kind of artificial intelligence that we're seeing around lots lately is something called machine learning or deep learning. Now, we're very lucky to be working with a research group called Maths4DL, which stands for Maths for Deep Learning. And one of their researchers is Kweku Abraham, who is also a postdoctoral researcher here at Cambridge. So he's our neighbor here at Plus. And to find out how this kind of artificial intelligence works, we asked him to explain machine learning.
Yeah, so machine learning, I think, is easiest to think about often in the context of games. And so you can think of kind of traditional algorithms. You tell the computer exactly what to do in each situation. So this is quite easy for a simple game like noughts and crosses, that you can say, if your opponent goes here, then you go here. If they then go here, you go here. But for something more complicated like chess, there's just far too many options to say really well exactly what to do in every situation. And you can kind of use some heuristics to simplify a bit. And so there are chess algorithms that are quite precise that are still better than people, but the very best ones now use machine learning instead. And the way that works is that you give the computer lots of flexibility and you give it a way to judge whether something is good or not, and a way to kind of improve its own algorithm. And so what it is it will kind of choose a move initially in a kind of fairly arbitrary way, and you can see, does it end up winning that game? And you teach it to kind of, or you allow it to teach itself to nudge towards the moves that won more often and the moves that lost less often. And over many, many iterations of seeing lots and lots of games played, it moves towards choosing good moves because they lead to the winning outcome more often.
And this is incredibly, almost surprisingly effective, isn't it? You wouldn't think that, this kind of nudging itself to the right answer, it does work amazingly well.
It does, yeah. It needs lots and lots of data. And so the key things that have really unlocked our ability to do this are having computers that can calculate things fast enough that you can kind of run these algorithms to improve, and also just having loads and loads of data that, ChatGPT was trained on most of the text on the internet. And if you have less text than that, then unless you do something much cleverer than our current ways of sort of improving these models, then you don't get something very meaningful out.
So it's so amazing that all of the things that we hear about as these amazing examples of AI, such as ChatGPT or these generative AI, they're all based on this concept of machine learning, where rather than explicitly tell a computer how to do a job, it learns it by doing itself, particularly by running through examples of something called training data, where it's got data it can work on to learn how to do a task.
Yeah, it really is amazing. So, given all this amazingness, is this it then? So, has proper artificial intelligence, as we used to only think about in sci-fi terms, has it really arrived? Well, one way of finding out is the so-called Turing test, named after the World War II codebreaker and mathematician, of course, Alan Turing. And the idea behind the Turing test is that if a machine can exhibit intelligent behavior, so that in a conversation, in an exchange with that machine, a human wouldn't be able to tell that it's a machine, then that machine has passed the Turing test. So we asked Kweku, does the type of artificial intelligence that we have now, does it pass the Turing test? And he has an interesting answer.
So I think in recent times people have wondered a bit whether the Turing test is the kind of best metric to use, because often the easiest way to pass the Turing test, and I quite like the articles of Tim Harford on things like this, the undercover economist, is to reduce the level of the human rather than to improve the level of the AI. And so for kind of arguments on the internet, often one of the participants is a chatbot, and people don't realize, because when you get very angry it's hard to kind of think logically. But I think also I think there are areas in which ChatGPT and other and successors, other things like that would kind of pass the Turing test or be close to, but also they're not kind of broadly applicable to everything in a way that we might expect for general intelligence.
So Kweku's saying that if someone's very angry, they find it very hard to be rational and logical and indeed spot a chatbot. But also, there still isn't any AI around that can fool a human into thinking the AI is a person on any task. They may be able to fool a human into thinking the AI is a person on some specific narrow task, but not in a general sense of intelligence.
And I'm quite glad about this, because it means that even if I do lose my job to an AI, I am unlikely to also lose my friend and my partner or my cat, because it's still impossible for an AI to replace my entire humanity. So, how is all of this mathematical? Well, the learning process that the algorithm goes through really involves producing a mathematical function. So it's a way of turning an input into an output. So if you take as an example an algorithm that can look at pictures and decide if the picture contains a cat, then the input is a picture, and it's represented by an array of pixel values, where each value just gives you the color of the pixel. So it's an array of numbers. That's a mathematical object. And the output is yes, it's a cat, or no, it's not a cat, which you can phrase mathematically as just a 0 or a 1 output. And similarly, if you think about a game where you're asking for the next best move, The current game situation, like say in chess, you can obviously encode that in a very mathematical way. And similarly, the output, the next best move, can also be encoded mathematically. And as soon as you're looking at turning mathematically encoded inputs into mathematically encoded outputs, you're really doing maths.
Yes, and the functions involved here are literally proper mathematical expressions like you might see in a textbook. And the algorithms that are used to create this, build these mathematical functions, use something called neural networks. And indeed, as you might think from that name, it takes some inspiration from the neurons in our brain. They have little mathematical functions, which we think of as artificial neurons, and these are linked together in these networks to build greater power of information processing, or perhaps in the stage of true AI, some kind of real intelligence. So these neural networks, they have internal parameters which are called weights, which you can tune. You can think of them as like knobs on a machine, and you can adjust the knobs to give you better and better answers and improve the performance. And there's a parameter for each of the little artificial neurons in the network. And in the learning phase, the machine learning algorithm tunes these weights, it turns these knobs to have the best value to give the most accurate answer. And that's the nudging that he spoke about.
Okay, so now we've had a very general way of describing machine learning, but there is also something called deep learning, which is a form of machine learning. So we asked Kweku to explain what that means too.
So deep learning then is a particular way of doing machine learning algorithms. It usually refers to neural networks, which again these kind of have weights. They're a particular way of taking a load of inputs, giving you some outputs that are then what's your estimate of whatever thing you're trying to find out. And deep learning, you kind of iterate this through a bunch of layers, so you kind of run the same type of algorithm a bunch of times before what you get out in the end is your final sort of guess at what's going on.
So the main idea here is this iterative process that's involved in turning input into output, which basically practically is saying that the neural network has layers. There's many layers, which means that this iterative process happens from layer to layer as it goes along. So for example, say your task, as we said before, is to see if a picture has a cat in it. So your input, your raw input, is this pixel values of the colors in the image. And the first layer of your neural network may start to spot rough features such as edges, the pixel locations of rough features such as edges in your picture. Then the second layer acts on those features that you've spotted and starts to spot arrangements of these edges. And as the layers go on, it gets more and more understanding of structures within these within the image. And the last layer finally just acts on these structures that the neural network has identified and just can give you the answer yes or no, is it a cat or not?
Yeah, and that's why it's called deep learning, because there are many, many layers, so it's deep.
Okay, the thing is, but why is deep learning so powerful?
Well, it seems to have something to do with that deepness. Remember that you're looking at a function, a mathematical way of transforming an input into an output. And there are interesting results about functions that you can actually prove mathematically. Here's Kweku again explaining some of the detail.
Part of our understanding for why they seem to work is down to just compositions being very nicely behaved. That deep neural networks are compositions of functions, and there's a result called the universal approximation theorem, which says that every continuous function, I think, can be approximated well by compositions, and you can prove some results showing somehow that even quite complicated functions can be represented quite efficiently using compositional structure.
Right. So even though the thing you're looking for is really complex, this function that's going to transform input to output, a neural network allows you to approximate it really well. And it's composed together of these simpler things, these layers of simpler things in the neural network.
Yeah, I think that's what Kweku is getting at. And there must be a lesson for life in there somewhere about breaking up difficult tasks into other chunks and iteratively performing them. I don't know. But anyway, I think it's fair to say that even the people who came up with neural networks and machine learning were surprised at just how powerful the method is. So maybe in some way there's still a bit of a mystery there about how it works so well.
So we were wondering if there's any limits to what we can do with deep learning. So we asked Kweku.
I think it's very hard to say. Yeah, I think the um, lots of the reason for the advances now are improvements in computational power, and I don't know, but we're maybe not too close to reaching our limits on computational power, and so insofar as these algorithms improve as you give them more computational power, then we can expect them to keep improving. Maybe there's some limits on how good the algorithms can actually go. Another issue is that the ones in use at the moment are often trained on basically all of the text on the internet, which means that you can't go much further in terms of giving them data to improve on. That really it's getting towards the point where you need to improve how you use the data rather than just throw more data at it.
And is that then also relevant to situations where just enough data, so much data isn't available?
Yeah, so there's some research on transfer learning, which is the idea that somehow you can train on a different problem, make an algorithm that's really good at some other problem than the one you're really interested in, and then just add a little bit of data and a little bit of training for the problem that you're really interested in, and maybe be able to do it. So like an idea of how to think about this, I think, would be that if you want to get a computer to be really good at some language, that there's kind of grammatical ideas that are similar between lots of languages, and so maybe training it lots to be really good at English, which is relatively easy to do because there's so much English text on the internet, then gives you some idea when you feed it some language that has far less text available. It already knows what kind of features to look for a bit, and so there's maybe some kind of ways in which you can mitigate having less data by doing some kind of pre-processing extra work. But certainly, I think for most problems where you don't have much data, we need to come up with different algorithms than the most successful machine learning algorithms, deep learning algorithms of the moment.
So Kweku is a postdoc at Maths 4DL, and we were wondering, what does he actually do every day? So it turns out he is working on something that is related more to statistics, which is about collecting data and then inferring from the data what's going on in real life. Now, there is this wonderful thing called Bayes' theorem, which helps you do this. So Bayes' theorem, it lets you update what you think you know about reality based on the data you have. So that's called your prior belief, what you think you know. And Bayes' theorem lets you update that belief in the light of new data coming in to get what's called a posterior belief.
Oh, yes, the wonderful Bayes' theorem, which is named after the Reverend Thomas Bayes, who came up with it such a long time ago in the 18th century. It's very useful in statistics. And here's Kweku with an example.
A kind of typical example from medicine might be that someone comes in and you have some prior belief on what their chance of having a disease is, and then you run a test, and so then you use Bayes' rule to update your kind of beliefs on how likely they are to have that disease. But so in that case, the prior might come sort of reasonably well defined because you might set it as the kind of base rate of that disease in the population.
So this ability to update your beliefs can again lead to an iterative procedure. Let's look at another example. Suppose I want to estimate the average height of people in the UK. Now, I could start by just looking at my own height. That's probably not a very good estimate of the average height of people in the UK because I'm just one person. So what I can do next is look at the average height within my family, and then I can use Bayes' theorem to update my previous belief about what the average height is. And then to make it even better, I can then look at the average height amongst all my friends, including family, and again update my belief. Then I could look at all my neighbors and friends and family and update my belief, and I could keep going, looking at bigger and bigger groups of people, bigger and bigger samples from the population. And as I take into account more and more data and keep updating my beliefs using Bayes' theorem, my estimate here should converge to the true average height in the UK. Otherwise, that process of iteratively updating my beliefs wouldn't really lead me to the right place.
And does it?
Yes, well, in this example, in this case of trying to figure out the average height, we have quite a lot of information. So we know that the heights follow what is called a normal distribution. So basically, if you made a histogram where for every possible kind of height or interval of heights, a 5 centimeter interval, say, or something, if you drew a histogram, so for each of them, for each height interval, you note down how many people are that high, then the shape you'd get would be the famous bell curve of the normal distribution, where at the tip, the tip corresponds to the height that most people have, which also in this case happens to be the average or mean height. And the tails sloping off to the sides, they just indicate that smaller and smaller and taller heights become less and less frequent in the population as they get more extreme. So we know that heights are normally distributed, and the only thing we don't know in this case is what is the actual mean, that is the average of the distribution. And here's Kweku again, telling us what we know about our updating procedure using Bayes' theorem in this case.
So you have your kind of assumed model, maybe that you assume this is your normal distribution, and you don't know what the true mean is. And I analyze, will your kind of posterior beliefs converge around the true parameter? So the kind of model is correct. There is some parameter for which a normal will fit the data, but it's whether your beliefs kind of will get to that. And that's kind of well understood if it's something as simple as so if you know everything about the model, so you know that it's a normal and you only don't know what the mean is, there's some theorems which tell you that your beliefs will converge to the truth and everything you do will be right kind of in the limit, provided you don't put sort of no weight on whatever ends up being correct. And so what I am studying in general is when the thing you don't know is a whole function, and then everything gets much subtler. It's much harder to kind of say what your beliefs about what the function is in advance. I could say a half chance of being between 1 and 2, and that's kind of fairly easy to pin down, but what's the chance of it being this particular function or that particular function? It's much harder to kind of describe beliefs.
So to summarize, Kweku's research is about working out if this constant updating using Bayes' theorem converges on the truth as you get more data, when the thing you don't know is more complex than the example we had before of finding the mean of a normal distribution. But how is this related to machine learning or deep learning?
Well, there's cross-fertilization apparently. On the one hand, ideas inspired by deep learning and neural networks to do with many layers and an iterative process, they are relevant to Kweku's work. On the other hand, when you're dealing with neural networks, as we said earlier, it's about tuning or finding values for those weights, those internal weights. But instead of finding a definite value for each weight, you can also aim to find a distribution of possible values, and you update the distribution using Bayes' rule. So this can get you then into similar situations as those Kweku investigates.
So, as we've often found in our adventures in mathematics, everything is connected. And as well as being connected, often the best ideas in maths research comes from connecting ideas from seemingly different areas of mathematics. We see this time and time again, and it really shows up here in this work with machine learning. That's all we've got time for in this podcast. We'll be talking more about machine learning and deep learning in an upcoming episode.
Yeah, and in the meantime, if you would like to find out more about artificial intelligence, machine learning, and deep learning, or indeed the Maths 4DL research project, we've put some relevant links into the show notes. And you can also go to plus.maths.org and search for those terms using the search. Thanks for listening, and bye for now.